Hello everyone, guten Tag. My name is Tom Moore, and I am an autonomy developer with ClearPath Robotics. And today I'm going to be talking to you about working with the robot localization package. So, what is robot localization? I should back up a little bit. First, can I see by show of hands who all is actually familiar with this? Okay, so quite a few of you could. Okay, so I apologize ahead of time. I'm going to kind of go over some things that might, this is going to be centered around the kinds of things that people ask on ROS answers. And then I'll try to move on to things that are a little bit more advanced. So just bear with me and try not to fall asleep. What is it? It is a general purpose state estimation package. So when we started writing it, the goal was to address a broad range of robots. We don't have any limit on the number of input data sources. So if you've got 17 IMUs, I don't know why you do that, but you can use them. Along with the large number of data sources, we also support 4 different message types. The odometry message, obviously if you have odometry message, it's just a conglomeration of a pose and a twist, so we support both of those as well, and then naturally the IMU. The state vector is 15-dimensional, so it's pose, linear and angular velocity, and linear acceleration. And so typically there are two different use cases. One is to fuse continuous sensor data, so data that's not subject to discrete jumps. And then that will produce a locally accurate state estimate that you can use for local navigation. Second use case is to fuse that same data with sources of global pose estimates. So something like a SLAM package, like AMCL, you can fuse it with those so that you can get a complete and accurate global state estimate. And it's also good for in those use cases, it's good for if you have infrequent global pose estimates, like coming from a GPS at 1 hertz, right, and you want to make sure you have a filtered state in between those 2 readings. It's very useful. So the nodes contained in the package, there are actually 2 filters, 2 state estimation nodes. The first is an implementation of an extended common filter, EKF localization node. The second is an implementation of an unscented common filter, UKF localization node. They both have identical interfaces. For all intents and purposes, you can use them interchangeably. Navsat transform node is kind of a sensor preprocessing node that's also included that allows you to take geographic coordinates and then convert them into coordinates that are compatible with your robot's world frame. So this allows you to directly fuse basically GPS data with your state estimate. Just to give a little more context about those 2 use cases that I mentioned earlier, I'm going to kind of show this graphic from the ROS nav stack that I got off of the MoveBase wiki. And slide it over here. The first use case here is basically sits right there, and I'll back that up. So your odometry source, right? You can replace it with one of the filters, and you can send all sorts of different types of data to it. Right, and then the second use case is naturally the one that fuses global pose estimates. So you can again feed that same data to it, but then also feed it the output of one of these other things that actually do kind of global localization against a map, or if you're taking in GPS data. I should mention that these ones at the top here, this really should be kind of an OR relationship. I don't really think you'd want to be fusing all 3 of those together at the same time. Okay, going to get into kind of preparing your sensor data here. This is true. You cannot spell prepare without REP. So ROS enhancement proposals, for anyone who may not be familiar, kind of useful for, in this case anyway, specifying standards. 2 very relevant ones are REP 103 and 105. Won't go into too much detail with them, but it's worth giving them a read if you are going to be writing your own driver and you want it to conform to standards. Chances are, if you're using a package that's already out there, the author probably already adhered to these, so you're fine. I will go into a little bit more detail about REP 105 on the next slide, though, because it seems to be a common source of confusion. We'll start out with the kind of 3 principal coordinate frames that are laid out in REP 105. There's base length, which is the coordinate frame that is rigidly affixed to your robot. There is the ODOM frame, which is a world-fixed frame, basically has its origin at your robot's start pose. And then the map frame, which for most intents and purposes is identical to the ODOM frame, except that the standards suggest that in the ODOM frame, your pose should be continuous, right? So you can use that for local navigation. Again, you shouldn't have any kind of discrete jumps in your pose estimate inside that frame. Just to kind of go over how these transforms work, so one of the filters will produce two things. It will produce an odometry message, and then it will also produce the transform from the world frame that you specify to the baselink frame that you specify. You can configure them. So that's how the ODOM to baselink frame works, and then that's if you set your world frame to ODOM. If you set it to map, internally, we also generate this map to baselink transform, but TF, because it's a tree, does not allow you to have two parents for a given node, basically, so you need to do this process whereby you take your internal transform from map to baselink and look up the transform from ODOM to baselink and use that to generate a map to ODOM transform. So the filters can handle both of these. So all pose data that you take in, so the stuff that comes in from the pose message or the odometry message, those are going to be transformed from whatever frame ID is in the message to the frame ID to the world frame ID. Twist data, likewise, is going to go into baselink. So now the only exception there is IMU data. IMU data obviously contains orientation in it. The way we handle that is the problem there is that IMUs are mounted with respect to some offset on your robot, right? And so that's the frame ID typically that people give. So they generate some static transform from baselink to the IMU frame. But then we need to use that information to kind of correct the orientation in the IMU. So if you imagine an IMU that you have that's facing left, for example, then in the IMU frame, if you go like this, it's obviously pitching, but yet the robot itself is rolling, so we need to correct for that. Okay. So just to drive that point home a little bit more. So if you have, this is your IMU message, and you want to actually use it, you're going to have to provide this transform from baselink to IMU link. If you don't, it's just going to ignore it. And in this case, you've got an odometry message coming in, and the frame ID is already set. You don't have to generate any transforms if those are the names of the frames that you specified. Okay, gratuitous math slide. This is kind of standard formulation for an EKF. People who are familiar with it will no doubt pick out the differences very quickly. Just wanted to point out a few things specifically about covariance matrices here. The first one is that there are three different key ones that you can specify. The first one is the actual estimate error covariance, which basically the error for your whole system, right? You can't specify it all the way through, obviously, but you can specify it at time 0. So this is especially useful if, let's say, you're going to be measuring a given variable in your state vector. Then it makes sense to set the diagonal value on this covariance matrix to something that's a bit higher than whatever the variance is on that variable in the measurement, because then it'll be fused more quickly. It'll converge faster. The process noise covariance matrix, so basically kind of dictates how quickly the error is going to grow in your system, but can be very difficult to tune. There are methods out in the literature. I tend to basically kind of hand tune this, tweak parameters until I feel that the error is growing at a reasonable rate in the whole system. And then lastly, and this is very important, the covariance and the measurements themselves is very important. So if you're sending out measurements that have all zeros in the covariance fields, the filter will deal with it. It's just going to give it a very small value. But you don't want that. You want to make sure that you actually get some reasonable values in there. Okay, so here's how you do coordinate frame specification. So you've basically got the principal frames, like I said, you can name them whatever you want, and then you can set the world frame to one of these two, to the map or the ODOM frame. And which one you set it to will change the behavior in accordance with that slide earlier that I showed from REP 105. So input specifications, I don't know anyone that's had quite this many inputs, but you could if you wanted to, just an example of what you're doing. I have personally worked on a project where we had 7 different inputs, including 4 different IMUs. So it's not entirely impossible. So basic input configuration. Okay, I could probably spend the rest of this talk and then another one going over just this, but I'll go over the kind of key points. So the order here is x, y, z, roll, pitch, yaw, velocities for those, and then linear acceleration. And so it's important in general to make sure that you are measuring across all of your different sensors, you need to make sure you're covering at least a pose variable, each of the pose variables. If you can't do that, cover one of the velocity variables, and if you can't do that, you're probably in trouble. So your covariance is going to grow very quickly. So if you look at this example right here, I've got an odometry source and I've got an IMU source. Nothing is measuring z or z velocity. And so what you're going to see is the variance on z grow very quickly, and then other correlated variables, you could see the same thing. We are measuring z acceleration, but again, that double integration is just going to cause the variance on that to grow too quickly. And so, one other thing I should mention is that you'll notice that even though an IMU, for example, doesn't measure x, y, and z, we have that in there just for consistency across all the sensors. So if you happen to set one of those to true, it's just going to be ignored. So then, here's another example where now we've got another sensor. We've got an ODOM0 source and an ODOM1 source. Both of them are measuring x and y. So this is a case where you really need to be careful and make sure that your covariance matrices are being set correctly, because if you've got two sensors, let's say you've got one that says I'm at 2.2 and one that says I'm at 10.10, and they both have a variance of 0.1, well, one of them's lying. You have to make sure that there's some overlap there. Otherwise, what's going to happen is as every measurement comes in, it's going to jump back and forth between the two. And I've seen this happen with IMUs especially, where the manufacturer will report some error rate on their heading, and what you'll actually find is that two different IMUs on the same vehicle that starts jumping back and forth like this. So one way to get around that, if you don't feel like fixing the covariance matrices on the messages, is to use this differential parameter. And the idea with that is that it will take a measurement at time t and then time t+1, and it will it'll differentiate between them and convert that to a velocity, and then feed that to the filter instead. So you'll get one of these. So you could do it with both of them. I usually just leave one alone and then turn the other one on the differential mode. But that gets around this problem. I'm not going to print the full covariance matrices here because they are 15 by 15. So, but you get the idea. This is just how you specify those two. Okay, I hope this meme isn't lost on too many people. So it's not. So I should point out I am not playing back entirely bag files. I am playing back the raw data from bag files, but I am running robot localization live. So let's see. Can you guys read that? Yeah. Okay. The first instance here. This is our ODOM instance basically, and so we're fusing the odometry, wheel encoder odometry data from a Husky and an IMU. And then you can see the specification there for what we're including. One other thing you may notice, did I do it here? Yes. You'll notice that even though the robot probably isn't going to give me any positive values for y and z velocity, I'm still setting them to true. And that's because the robot cannot actually attain instantaneous y and z velocity. And so the zero measurement that I'm getting is actually valid. And so it's worth fusing. So a bunch of other settings here, which I won't get into right now. There are even more advanced settings that aren't even in this file. Feel free to come talk to me if you're interested. And then here's the second instance. That's the exact same thing, except we've got this added ODOM1 source, which comes from navsat transform node down here. Our IMU, the IMU in this case was offset, so I had to add that in there. So I want to preface this demo by saying that this was run on a very nice Husky with the world's worst IMU. Well, not worst, okay, most broken IMU. So the heading that the IMU reporting, it's kind of all over the place. There's a lot of magnetic distortion in the place we were running, and then also the IMU itself was just kind of borked. So you'll see it come out here, but it's an important point, and it's kind of it's actually a good talking point. Okay, so a few things to go over here. First of all, the red, I believe, is the ODOM frame version. The red is the map frame, but because RViz is cleverly transforming one to the other, they overlay each other completely, which is why it doesn't seem that they differ at all. But in reality, they are differing from one another and diverging from one another. And this blue thing here, this is the output of navsat transform node. So that's getting fused with one of the status. And so I can show you, and I can explain this too when you start seeing how it looks a little off. This is when you're looking at the output of the map frame version, right? So every time you get a GPS measurement, you see the robot kind of jump a little bit. And you can see the kind of difference between the way the robot thinks it's headed and the way it appears to be headed according to these GPS points. So that, again, is a result of just this kind of IMU not being quite right. It makes an important point, which is that one of the powerful things about Kalman filters in general is that they can deal with noisy, terrible data, and especially when you have a situation like this where perhaps you know that your IMU might not provide very good orientation data, you might have another IMU on there that does. So you can use them both, or you can turn the orientation off on one and use its angular velocity instead, just use the gyro data. So it gives you a wealth of options. Okay, NavSat transform node, I already went into this a bit. I'll just cover it a little bit more. So obviously a lot of robots make use of GPS receivers. The idea here is the problem is trying to get that data into your robot's world frame. So good solution is to first convert the GPS coordinates into UTM coordinates. And since we know how the UTM grid is oriented, we can use a world reference heading from an IMU along with our robot's current pose to compute a transform from that UTM grid into our world frame. And it seems to work pretty well. So the three inputs you need are the odometry message. I'm still using this in the wrong format, sorry. Oh, bad. Rookie mistake. Talk amongst yourselves. Okay. That's interesting. Okay. We transform all future GPS measurements using that same transform, and then we can feed that back into the filter. And I know that seems a bit like a circular relationship. It's really not, because at the time that NavSat transform node receives that first measurement from the odometry, from the EKF output, it doesn't actually have any data from the GPS included in it. So once it receives that, it generates the transform, and from that point on, it just uses that statically. So these are the required input messages. Relevant settings, magnetic declination for wherever you are. It's important to set yaw offset if your IMU does not report 0 where you think it should. 0 altitude, basically the altitude coming out of there will be set to 0. That UTM transform I mentioned to you, you can use this setting, broadcast UTM transform, to broadcast it and use it elsewhere if you want. And then publish filter GPS is useful because what it does is it goes the other way. It takes your fused data and then spits out GPS data instead. It's very useful for plotting on live maps or MapViz, for example. Typical setup. For NavSat transform node, I'll just fly through this. Here's the ODOM instance, the map instance. These are all the inputs to NavSat transform node, and then it spits everything back to the EKF. Final point here, robot localization works on a broad range of robots. On the left, you'll see a tiny little RC car robot I worked with that has an O-droid on board, and it works just fine on that. And then to this is Auto, ClearPath's latest robot, so definitely runs the gamut. Thank you. The question was, can we estimate gyro biases? And the answer is currently not yet. It's definitely a feature I'd like to see added. Sorry? Absolutely, yes. Yep.
Do you have a recommendation of
process noise? No. Aaron's favorite question. No, the short answer. Again, this tends to be a hand-tuned thing for me. I know there are methods in the literature for handling that. I have not personally ever actually implemented one of them. It tends to work pretty well, as is. So hold on, let's go back. So you're asking whether or not we need the IMU data to go into NavSat transform node?
Yes.
Okay, so you... ODOM to base link. Yes, yes, oh, I'm sorry, if you need the IMU data from, no, absolutely not, no. I mean, it's just whatever frame your map happens to be. It's okay if you don't have one. I mean, I don't know why you wouldn't use it, but no, you don't need that.